You know, every quantum computer has this invisible engine, right? It's a piece of software that's absolutely essential for making it all work, translating our abstract ideas into physical reality. Today, we're pulling back the curtain on that engine, the quantum transpiler. All right, so let's kick things off with a really fundamental problem. Imagine you've designed a brilliant quantum algorithm. On paper, it's flawless, theoretically perfect. But then you go to run it on some actual quantum hardware and nothing. It just fails. So what gives? This is the central challenge that pretty much every quantum developer runs into.
Well, the problem is something we can call the quantum reality gap. See, on paper, your algorithm lives in a perfect world. You assume that every single qubit can talk to every other qubit, no problem, and you can use any fancy quantum gate you can dream up. But in the real world, the physical chip has a fixed layout, like a grid where each qubit only has a few direct neighbors, and it can only perform a very small specific set of operations. That's its instruction set architecture, or ISA. It's the hardware's native language, basically.
So how do we cross this gap? Well, that's where the transpiler comes in. It's a special kind of compiler that takes your ideal abstract circuit and transforms it into a totally new circuit that's functionally the same, but it plays by all the real-world hardware rules. And what's really crucial here is that it's not just translating, it's actively rewriting and optimizing the circuit to give it the best possible shot at succeeding in a super noisy environment.
So how does it actually pull this off? You can think of the whole process like a journey that every single quantum circuit has to go on. It's like a 6-stage gauntlet it has to navigate to get ready for the hardware. Let's walk through each one of these stages.
Okay, the journey kicks off with initialization. This first stage is all about getting everything on the same page. It takes any complex, high-level gates you might have, like a 3-qubit Pauli gate, and it breaks them down or unrolls them into a simple sequence of 1- and 2-qubit operations. This just makes sure that every other stage of the transpiler is speaking the same language, working from the same set of basic building blocks.
All right, next up is layout, and let me tell you, this step is huge. The transpiler has to figure out which of your abstract virtual qubits should be assigned to which real physical qubits on the chip. This is this giant complex optimization puzzle because not all physical qubits are the same. They have different error rates, different fidelities, so getting the layout right can make a massive difference in whether your algorithm works or not. Okay, so once the layout's locked in, we hit the routing stage. What happens if your algorithm says qubit A needs to talk to qubit Z, but on the actual chip, they're on opposite sides? That's what routing fixes. It cleverly inserts special operations called swap gates, which literally move the quantum states of the qubits around the chip until they become neighbors and can finally interact. Now here's the catch. Finding the absolute best, most efficient way to do all this swapping, well, that's what's known as an NP-hard problem, which is just a fancy way of saying that as your circuits get bigger, the time it takes to find that perfect solution just explodes. For anything other than the tiniest circuits, it's basically impossible. And that's exactly why the transpiler has to use clever shortcuts, or what we call heuristics.
So how do these shortcuts work? One of the most important ones is called saber swap. First, it finds a gate that's stuck, one that needs to connect 2 qubits that aren't neighbors. Then it looks at every possible swap it could perform to bring those 2 qubits closer together. But it doesn't just pick the most obvious one. It has a look-ahead window, so it's playing a bit of chess, thinking a few moves ahead to pick the swap that helps out not just now, but for the next few gates down the line. It picks the best one, inserts it, and then just repeats the process.
Okay, after all that routing, we get to the translation stage. Think of this as the final official translation. It takes every single gate in the circuit, which might be a generic one like a C0, and rewrites it into the hardware's very specific native language. For instance, some IBM hardware doesn't use C0s natively. It uses a different gate called an ECR gate. This stage makes sure the circuit is speaking the exact dialect of that one specific quantum processor.
All right, stage 5, optimization. All that routing and translating often adds a ton of extra gates, which makes the circuit longer and way more prone to errors. So think of this stage as the cleanup crew. It scans the circuit over and over, looking for anything redundant. Like if you have 2 gates right next to each other that literally just undo what the other one did, poof, they're gone. The goal is to make the circuit as short and efficient as humanly possible.
And that brings us to the final stage of the gauntlet, scheduling. This is where the abstract list of gates gets turned into a concrete nanosecond by nanosecond execution plan.
It assigns a precise timestamp to every single operation, telling the hardware exactly when to fire each microwave pulse at each qubit. This step is absolutely critical for more advanced techniques like the error suppression tricks we're about to talk about.
Now, this whole 6-stage process can be, well, more or less intense. And the cool thing is you, the user, actually have a dial you can turn to control just how hard the transpiler is going to work on your circuit.
And this table here lays out that trade-off perfectly. You've got 4 optimization levels, from 0 to 3. At level 0, it's super fast, but it does the bare minimum. But if you crank it all the way up to level 3, well, it's going to take a lot longer for your computer to chug through it, but it uses some really advanced math to find the absolute most efficient circuit possible. It's a classic trade-off, your time versus the quantum computer's performance.
So why are we so obsessed with getting rid of these swap gates? Why does it matter so much? Well, it really all boils down to one simple, brutal number: 3. You see, a swap gate isn't a native operation. On the hardware, it has to be broken down into 3 CNOT gates. And since CNOTs are one of the biggest sources of error on a quantum computer, every single swap you add is like injecting a triple dose of noise right into the heart of your calculation.
Okay, so this brings us to a really cool, more advanced role for the transpiler. It's not just a translator anymore. It's actually a proactive defense system against all that quantum noise.
A fantastic example of this is a technique called dynamical decoupling. Think about it. During your circuit, some qubits are busy, but others are just sitting there, waiting their turn. And while they're waiting, they're like little magnets for noise. The transpiler scheduler can spot these idle times and cleverly stick in a special sequence of extra pulses. These pulses don't change the final answer. They just cancel each other out, but they act like a shield. They're constantly refocusing the qubit, kind of shaking off all that environmental noise.
So where does this all go from here? You might think that as the hardware gets better and better, the transpiler's job would get easier, right? But actually, it's the opposite. Its role is becoming more important than ever.
And this chart right here shows you exactly why. When you're transpiling a really complex circuit, a mind-boggling 99% of the time your computer spends is chewed up by just 2 stages: layout and routing. That's it. That classical computation time is a massive bottleneck.
So to fight this, the whole industry is starting to shift towards some new solutions. Developers can now just offload this heavy lifting to powerful cloud-based transpiler services. And what's really, really cool is that these services are starting to use experimental AI. They're using machine learning to try and find even smarter ways to map and route circuits, maybe even better ways than humans have thought of so far. So at the end of the day, the transpiler's job is safe. It's going to remain that critical bridge between our ideas and the physical world, making sure that as our algorithms get more and more complex, they can always find a reliable home on the real, messy, physical hardware we have today and the hardware we'll have tomorrow. And all this leaves us with one last question to chew on. As our quantum hardware keeps improving, with more qubits and better connections, will the transpiler's tough job finally get a little easier? Or will it just have to get even smarter to keep up with all the new challenges that are just around the corner?